Hi, everyone. I'm Timothee Verdier from the machine learning group, and I'm developing, among other things, this LLM functionalities for the Wolfram language. Right, and so today I try to guide you in a tour around the programmatic functionality, because we also have those more interactive functionalities, such as chat books that you've probably already seen. And today it's more like under the roof type of things with LLM functions and LLM synthesize with all things that we can derive out of those. So first thing, a quick outline of the presentation. Just a quick introduction about large language model and how to use the pre-trained one in our system with very core and basics idea about how they work, because that's important to have this information to take the most out of it and avoid the very classic issue that you can have when you work with LLMs, large language model again. Then quick description of the workflow for programmatically working with LLM in the Wolfram language. Quick description of the changes that this new big burst in developing field of LLM have put to the neural network world with pros and limitations. And then we're gonna dig deeper in the different use cases. I'll try to orient as much as possible this presentation on real case usage. So mostly it's going to be about prompt engineering and all the tool in the Wolfram language to all the different versions of prompt engineering that we can offer to control the language model generation. And so that's conditioning with the LLM function, few-shot learning with LLMExampleFunction. All that will be explained, and eventually some even richest examples of generation with things that are more multi-step tools and chats. Right. So this is the plan for the journey, and here we go with a pre-trained language model with the very 2 lines of introduction about how things work and what a language model is. Really first principle. So if you were to train a 3-token language model, which we can call it a SLM, a small language model, you would start by submitting sequences of those 3 tokens, hiding 1 token in those sequences, and prompting the system to guess, to provide you with to predict probabilities for the token that is hidden. That is, given the sequence full bar, nothing bar, what's the probability for the next token, and the next token can be full with probability 50, bar with probability 33, and again space or nothing with 70%. And training is all about tuning those values. You have a prediction function, which is the language model, and the language model, it's all about predicting those values, those odds here. And after you trained it, you can generate using this language model, and the generation is actually quite simple. you start from a state that is like part of the sequence, can be nothing or some seed sequence, and you predict using the trained language model the probability for the next token. And when you have those probability, you can just sample one of those probabilities. That is, if you have a 6-face die, a classic die from 1 to 6, then the foo token with probability 33%, you will select it if you get a 1 or 2. A bar with probability 50%, you will select it with a 3 or 4 or 5 when you roll the die. And depending on the outcome of rolling the die, if you get a 3, you will add the new token bar according to those rules. And you will end up with a new state foo bar. And you can carry on generating the sequence this way. So if I have foo bar, what's the probability for the next token? It's new predicted odds. And you roll a die again, and depending on the outcome, you generate the next token for the sequence. So those language models, either small or big, are really kind of are trying to reproduce language by figuring out the conditional probabilities. And you train them with the big LLMs are trained with basically all the text available on the internet or at hands, so that they become very, very well fine-tuned on what's the correlation between words in the language, and they can generate text that really looks like what we're used to with natural language. So let's not forget about it. Just keep it in somewhere for further use, and assume that we have such a resource. We have a trained LLM, a big one, which has seen tons and tons of texts, and now we can provide these LLMs that we use as a black box with, for instance, a fragment of Romeo and Juliet play by Shakespeare, and use this seed text, provide this with an extra information to LLM synthesize, which basically connect to a LLM. This by default is going to be the OpenAI one, and ask it to complete the text. So the text is the context is a fragment of Romeo and Juliet play, and here some instruction about what to generate. That is a short fragment of play imitating previous style, with Juliet and Romeo talking about artificial intelligence and with a machine can love. And if you have access to the LLM, you see that it's doing a pretty good job to write in Shakespearean style, with Romeo and Juliet discussing about machine herds. And you can obviously change this text by just either restarting the process and doing a different sampling, rolling new dice, if you prefer, or just changing a bit the probability. And all this is achievable using the LLM evaluator option from LLM Synthesize, where, for instance, you can put temperature control, how much you flatten or you pick the distribution of probability. That is, you will focus on the largest probability or just flatten them out, and the models that you want to target. For instance, we can go for a different model, a smaller model, GPT 3.5 Turbo, and also just ask for 100 tokens maximum. And if we do that with a higher temperature, the output should be much more random. That is, you see that we start to have sequence of characters that escape from the initial style, and we are exploring much further the probability space, even bit too much, looking at what's produced and generated. And so those model and this kind of very basic generation process is at the heart of the last revolution in the machine learning fields, because this just bridge a gap that was really hard to address so far, which is how to present information in natural language, and how to kind of imitate human language and reasoning with a machine. So obviously, the bigger the model, the better the result, especially it has been trained with as much text resources as possible. And so it's kind of hopeless to train those models on a local machine yourself, and you will need a service provider which give you access to such a model remotely. And for this, you will need to either set up a connection, for instance, in those settings here, where you have all the settings to access the service you're interested in, and you can register new ones, or just by using some low-level tools like system credential. And if you have OpenAI API key register here with the key that is provided by OpenAI, everything should work. Right. So the new workflow for working with LLM is quite different from what used to be in the neural network world. We used to gather a lot of data and train the internal function ourselves, and then refine the data. And you can forget about this. Just find a few representative examples. Choose your generalist large language model, like the service provider you prefer, and you just prompt it with the correct, which is where the art is now moved to. You prompt it with the correct seed text, and you're getting some generated results. You test to see whether it corresponds to what you want, and you will enter this loop where you will try to improve the prompt, test it again, and so on until you're satisfied, and then you can set a proxy for the service provider and just deploy your prompt as a function. So one basic example of using this LLM synthesize function to classify feelings on movie review, to deliver stars for movie based on the review. It's just prompting by saying that, well, one classifies the overall sentiments of the following movie review as positive or negative, and then say input is going to be this slot here, placeholder, and then sentiment is going to be, and we ask the model to complete. And because the model has probably seen a lot of movie review data sets, this input and sentiment is going to be filled appropriately. Also, we hope. Let's evaluate this function on something saying incredibly good movie, and see what the answer is, positive. And with one line here, this movie was not entertaining at all. with just one line here. We have a sentiment classifier for text. We know about rich and subtle, which is not those movie review, but it knows a lot about the language, and it's probably better than anything you could have trained with available data sets, even specialized one on movie. So obviously, this revolution makes things extremely accessible. It democratizes the use of machine learning based solution. It's as you can see, it's very expressive. That is like with one sentence, you can have working prototypes and even production ready systems. Even though things are not fully explicit, you can basically trust the language model to figure out what you want based on the context. It's very flexible also based on that. It has some common sense. It can generalize well, and when it works, it's extremely performant. Also, arguably, because that's you rely on the external service provider, it can be very performant in terms of optimization of the computation, because you have dedicated machines and very optimized generation process, which are hard to achieve if you just deploy your own neural network and on your premises. But as drawbacks, it can generate completely awkward failures. You don't have much control over it because you use it as a black box. It can hallucinate some knowledge, some results that is basically generating some random values for whatever question you ask. Because you use a service provider, the consistency is not guaranteed over time because models are changing, and it can affect the results. It can be very sensible to very small changes in your prompts. You have security issue. We will see as there was on especially when you don't control the input texts, and it's the clients that decide whatever he puts in. Training, data leak, and copyright are more on the service provider side, but they can be a concern. And you don't control much the training data. On top of that, you have the general machine learning risk, biases, ethic problems based on the data that were used, and a dependency on the service provider. So one way to kind of reduce that is to offer connection to as many service providers as possible, so that you have this freedom to just reuse the final layer, keep the interface, and switch to another service provider if you're not happy with the one you started with. So you see, there are pros and cons, and in order to take the most of it, you need your work starts with prompts. A good prompt, a good text is conditioning the generation of the returned text of the LLM, putting the LLM in the right context to generate exactly what you want. And because it's quite boring to just wrap LLM synthesize in a function like this, and because you want to just have the input text evolving with your inputs, we have LLM function, which basically takes a template and generates a function that you can evaluate on some inputs. So this is basically generating the prompt opposite of slow and feeding it to the LLM as if it were like acting as a function over its argument. You can map it and see what the LLM think about the opposite of slow, high, and side. See that's fast, low, and happy. And you see that it's quite versatile. It can even define an opposite for color, which is probably the complementary color. And what LLM function is just a template within LLM synthesize. Internally, it's gonna call LLM synthesize, but it has this icing on the cake, which is a final interpreter, which by default interprets returned value as strings. But you can tell that you want the return value to be considered as color, and now this new version here is interpreted result as color. So if I now ask opposite of blue, it will return the orange color object, which is very useful because now everything is integrated in the Wolfram language, and you can use this function as any other function in your programs. You can also tweak the input interpretation by having this insertion function that tells you how inputs of your LLM function should be considered before insertion in the slot here. So saying like you want image identify to act on the input and then transform into the result, transform into string, you can use an image as the input of your LLM function. Is going to use image identify, pass the string, the resulting string to the LLM, and the LLM will have to say what's the opposite of a monkey or of a mandrill. And so it takes a little while to have an image identify and the LLM call in a row, but yeah, you see, this is the LLM answer. So it's quite powerful and versatile. And the result of such function greatly depends on how good your prompt is, and in order to be flexible enough, you can combine those. So if you're interested into standards units and ask for the SI system above a given quantity, the LLM will probably give you a list as answer, right? Exactly like this. But in the world of computation, you want things to be formatted, like ready to use. And so providing a list of prompts to LLM function, this slot is going to be filled with this argument, but this second prompt to asking the LLM to write all answer as a JSON, standard the Java outputs, JavaScript outputs, you'll see that it will transform the LLM behavior to generate the JSON string. And now, if you think back about the interpreter argument, the second argument of LLM function, well, we say we have a JSON output, which is currently just a string, right? But a string that can be passed into JSON. Let's use a JSON interpreter and rerun exactly the same query. And here we are with a valid Wolfram Language list. And that's and you can specify, if you're not happy with a built-in interpreter, you can obviously go even further in details and use whatever function you like. So after the JSON interpreter, which is basically returning this list of strings, I will transform this list into association and map to expression on the return value, and here is the association with actual numbers, right? But as you may see, there might be also a bit of fluctuation in the generated outputs if the prompt is not clear enough. So that's that's covering basically all the aspects of LLM function. And as we mentioned, prompts are very important, and so we provide a repository of prompts, which you can access using the built-in LLM prompt and with the name of the resource you're interested in. So if you were at the presentation of the chatbook, you already have been introduced to persona, which basically acts as personality for the LLM generation, and we have this William Playwright character that's kind of mimicking Shakespearean style. And you see the LLM prompts retrieve a template object, and by applying it to actually nothing, you can just get the text inside the templates. That is one prompt that kind of force the LLM to adopt to write like some character and to fix the style of the answer. And you can also submit to this repository to kind of grow the library of possibles. You can have prompts that takes some variable input, just like the functions. And so you see that if we call the prompt translate, it takes two parameters. It translates the second parameter into and filled with a 1. So if we use translate with French, it's going to say translate something into French. If we use one sentence here, you will end up with a prompt that tells the LLM to translate whatever you put there into French. And this could be so you see you have access to the raw template object, and you can tune the text at your will, but you can also directly want the function form of this object, which is LLM resource function, and you can ask it to translate really in French, and it will output vraiment as expected. Also, you may be interested by actually plugging those prompts into the core function, which is LLM synthesize or the chat function. And you can do so using the LLM evaluator option of those objects. And if you do LLM synthesize on the default model, here is what you get. So, sorry for that. But if now you use the William Playwright prompt as a system prompt to start with, you will get probably a different style in the answer, because the LLM is coping with the prompt that we just see here, asking for Elizabethan words and writing in iambic pentameters, which you can check here. And LLM synthesize also have some special property to retrieve different parts of the generated output, which lets you and prompt delimiter value in the LLM evaluator, which that you check basically the full input that is submitted to the LLM. You see that there is this first prompt from the LLM evaluator with then the prompt delimiter used, and eventually the input that you entered as first argument here in LLM synthesize. Right. So having one prompt, or just catenating a few prompts together, all of those prompts being instructions, is useful, but it's not always sufficient in order to condition the LLM to generate what you want. And in more sophisticated cases, you might want to kind of hint the LLM about the typical output that you want. And because one example is worth 1,000 arguments, you will rather provide an example of what you want instead of a long explanation. And for this, we have a variant of LLM function, which is called LLMExampleFunction. And that kind of extend a bit this by providing a template for generating the prompt. So if your instruction is to remove the vowel from the text to return the consonantal skeleton of words, that is words without vowels, that's a complicated way to say it. You could instead, or on top of that, provide examples of what you want. Chemical is CHMCl and so on, right? And now, if we provide the list of the instruction and the example to LLMExampleFunction, we get a new prompt that is automatically generated by LLMExampleFunction, which the instruction and few examples. This is known in machine learning as few-shot learning, like providing example of what you want. And you can apply this example function, which is now a classic LLM function, as we saw, with this new prompt, on some text and see how it does at removing the vowel. And since this is a presentation about language, it's a kind of an example to prove some interesting properties of our own brain and language, which is that you can basically figure out the meaning of a text without the vowel. Only consonant kind of bears a meaning in many languages. There are languages which actually don't have vowels, or just add it for the sake of oralization. And one way to demonstrate this, let's say, a statistical property of the language is to ask the system to kind of, just by reverting the example, to kind of try to generate, to do the reverse transformation. And that's the add vowel function, where I just reversed the initial list and the instruction, which now is quite impressive and works very well. And if you are curious, you can try the same with add consonants, which is kind of the opposite way of doing things, where you remove you try to add the consonant when you have only the vowel, and you will see it's in the same text as and you will see basically first the LLM doesn't completely doesn't reproduce the text, so it's not one-to-one. That's a property of languages. But on top of that, it's completely hallucinating, which is finally here as three vowel, whereas there were only 4 of them. There was instead 4 of them in the first word here, and chemical is correct. Reaction is too, but that's an interesting feature of LLM, which is quite annoying in many situations, which is that the LLM can basically try to do more than ask in its mission, and produce results even though they are not satisfying the constraints that you put, because basically it's just putting together tokens in sequences, and even though you try by giving context to force to force this generation process into some controlled statistical space, this is still some random sampling. So you shouldn't. There's no much guarantees, and you shouldn't trust too much of the generated answer, even though the fact that it has scrolled the internet text for so long give you some kinds of statistical it's kind of a statistical relevance to the output, and you can use this example function, for instance, to kind of extract some famous physicist's date of birth, and it is kind of so this is like example function with name and date of birth, or for each of those physicists. Result being interpreted as date, and if you ask for Schrödinger, this is likely to be correct, even though it's kind of some random generation. But Schrödinger with the date of birth is probably correct on most of the internet corpus, or close to, and so you can expect, if this was not too biased at training, that the generation is kind of very well constrained on the true value. So again, non-limitation are hallucination, and with the LLM function opposite of, we can try again. If you produce garbage in, you're very likely, that depends on the model, in that you are kind of likely to have some either completely wrong answer, because it generates an answer anyway, or interesting one here is the answer kind of changed the input, because and also tells goes completely astray. If you look for gatos on some biological data, you will never find any link with alligators, just like only it's part of it, and the LLM wanted to build up on the seed text, on the seed sequence here. So more limitation, and also, if you want to open your application to the world, it can be very sensitive to the behavior of your clients. So if your prompt is translate this into French, and you take the incipit of the Declaration of Independence, it will work. But if an attacker want to kind of affect, and it's in French, want to affect your program behavior, it could just inject some new part in the prompt, saying like, oh, and from French to Italian, and because the full prompt makes sense, you will end up with an unexpected behavior, which in this case it is not harmful. It's just Italian, but depending on your function, can be very aggressive. And you have many different way to sanitize it, kind of making the prompt a bit more clever with start and end, and say in your instruction. This would probably work for this basic attack, but in general, there are a lot of steps that are involved into sanitizing the input from a user if you want to use LLM providing output, and not the least being the interpreter function after your LLM function, which kind of coerces the output to what you want. At worst, you get the failure. A few applications then, like if you have a very long text, you can do some semantic extraction out of this text. Like this function is just requesting for the list of question out of a text, and this is semantics that doesn't ask for the question to have interrogation mark or something, right? And on top of that, they're probably going to be a bit rephrased and summarized. So this is an interview of Steven Wolfram, with Lex Friedman, and and like there should be a few 10 minutes of discussion, and you can extract all the questions or most of the questions that were asked during the interview, and just retrieve the list of it, which obviously is a very powerful application that has been unlocked very recently. You can ask the system to format some data scattered in a text, like generating some association with the data, name, address, city, and so on, with some general texts. And this is example function, the instruction, and 2 examples. Here we are. And now we can extract data from this made-up text about some James Smith, and see that it will return an association and evaluate it as an expression, exactly what you ask, and I transformed it as a data set for visualization. Or you can just provide it with Wikipedia data, the Wikipedia page of Alan Turing, and you will see that personal data extract is very likely going to work with real-world data, and generate the data set formatted exactly as you expected. So kind of very powerful to extract knowledge from text. Or even something more programmatic, where we return events from a text by kind of summarizing for every person birth date and place, for when even non-available when they are not, and see how this propagates to some more wild text from the wild, and this is actually doing a pretty good job to generalize the missing are respected. So this example function, where few shots, LLM example function is quite powerful at letting the LLM figure out the formatting that you want from example. And you can even use the data to generate Alan Turing related historic line. So again, and or just generate some without using Wolfram documentation, generate some code for primitive of cos 1 divided by t with your expression. I really recommend you to use held expression in LLM generated outputs instead of just expression, so that you can control the result before letting it evaluate. And this is just Mathematica evaluating this. Okay. Last information. Sometimes single shot step like example function and LLM function are not enough, and you might get more interesting results by pushing the LLM to kind of explain step by step the detail of what looks like a reasoning. LLMs are probably not reasoning. They don't have feelings, but they're very good at mimicking those. And when you're very good at mimicking reasoning, you can get, if you're lucky, or if you're if you well conditioned statistically, you get it right. And so for solving math problem involving a little bit of reasoning of calculation, these are 2 examples I want that you can run when I was providing example of just the results of low grade problems, and a new question with implying addition and subtraction of numbers, and got a completely random result well, not completely random, but very confused one, and prompting which is wrong, and prompting the system differently by showing by actually providing the full reasoning as an example. Instead of providing a random number, the system just explain explain the step-by-step reasoning and get the right answer. So prompts and how you write them are very important in order to get some efficient output from an LLM. This kind of chain of thought prompting is effective only on very large language model. Sadly, it's you need to scale up to get results, and exist under as many variants as there are people, because you can always find like a different way to express those, how to change things, how to combine them, and so on. But forcing the system in your prompt to kind of expand the step-by-step, the generation of the solution is often very effective. If and one step further in multi-step generation is when you kind of want to guide the LLM to generate the right output in several steps. And the best construct for that is chat object, where you have a real conversation, yet everything is everything is programmatically accessible. You don't need to click or copy paste, and so you can start a conversation here using chat evaluate on your conversation, adding one message, and very similar to the chat book interface that you've seen. You will get a chat object which you can extract content from, and so have a kind of a conversation and help the system figure out what you want in a more interactive way, or just branch out depending on the system answer to have different cases in a program. And last but not least, tools. Like, as soon as you have multi-step and start this conversation, you can think about being more in kind of cope with hallucination by providing the system with the answer you want, either to circumvent its limitation. And something to know is that LLM are very bad at counting. So whenever there's some counting operation to be done, you better do it on your locally on your side. And so we have this LLM tool that just lets the system submit some query locally. For instance, here, counting the numbers of letters in the word character, it can basically submit character to the string length function here, because I provide him a tool which is this SHA tool, and so this is now multi-step. You see there an interaction. The progress monitor starts, disappear, and then start over because there are some exchange. And this 10 value here was actually evaluated on my computer. So the LLM will generate a request sent back to my computer that LLM synthesis will process and then feedback. So if we return all the properties of the process, you will see that there was not only a text completion, but some added prompts about how to write a request, and some and here you can see and here you can see that there was also some tool requests with string being set to characters, and some tool response that correspond to the an exchange between the LLM and my computer. And you can use it to more sophisticated question, like returning some travel distance value in order to let the system act as an assistant and let Mathematica figure out the math, so for a question, which city is closer to New York, Springfield, or Providence, you don't expect the LLM to know the answer. But you can see in the completion text that it kind of submitted 2 requests to my computer, travel distance from New York to Springfield and from New York to Providence, and at the exact value. And so it could answer. And those tools, you can either write those yourself, naming them with an indication for the LLM of what they do, the functions that you want to be locally run, and the signature of the function. From is going to be interpreted as a CT and to also before being fed to the travel distance function. And or you can submit and get those from the repository. So if you use LLM resource tool documentation lookup, then your LLM has access through your computer to all the Wolfram Language documentation, and you can ask questions such as, how can I compute Taylor expansion, which technically use the series function, not that easy to find out with a basic search. Right. And here a few more information about all the extent of the tool system. You can have several inputs that are interpreted as different as to different type. So this is an example of actually using series to compute Taylor approximation, but let the LLM figure out the right parameter for the functions. And if you want to evaluate a tool locally, like the travel distance one, which we just had, you can use this JJAP LLM tool response, the tool you're interested in, or a list of those, and submit a request that looks like what the LLM should return in order to get the answer. Like a request to city travel distance, this tool, from New York to Springfield. And this should provide you with this LLM tool response object, which can be transformed back into a string and sent over to the LLM. Right. And this is kind of the end of our dense journey through the prompting engineering and programmatic access to the LLM in the Wolfram language. Thank you very much.